So today we are going to learn about GNSS satellite. What is GNSS satellite? So GNSS or Global Navigation Satellite System refers to a constellation of satellites providing signal from space that transmit positioning and timing data to GNSS receivers. The receivers then use this data to determine location. By definition, GNSS provides global coverage. An example of GNSS include Europe's Galileo, the US NAVSTAR Global Positioning System or GPS, Russia Global Navigation Sputnikova Sistema or GLONASS, and China Beidou Navigation Satellite System. The performance of GNSS is assessed using four criteria: the accuracy, which is the difference between a receiver measured and real position, speed or time. Second, integrity, a system's capacity to provide a threshold of confidence and in the event of an anomaly in the positioning data. Third, the continuity, a system ability to function without interruption. Fourth, availability, the percentage of time a signal fulfills the above accuracy, integrity, and continuity criteria. So this is the comparison between a GPS from United States of America and GLONASS from Russia. If you notice, the altitude for GPS or GNSS satellite is on 20,000 kilometer in altitude. It is the middle of orbit or MEO. So, have you ever wondered how your GPS receiver works? Okay, so they use a technique called trilateration. Okay, trilateration involves measuring distance. So, how does the GPS system pinpoint your location using trilateration? Okay, let us use our imagination. Uh, Try to imagine three satellites on orbit, and using a simple two-dimensional example that we have three GPS satellites, each with a known position in space. The first satellite broadcasts a signal that eventually hits your GPS receiver. We don't know the angle, but we do know the distance. That's why the distance forms a circle equal in all directions. This means your GPS position could be anywhere on this circle at this specific radius. What happens when your GPS receives a second signal? Again, this distance is equally broadcast in all directions until it hits your GPS. Until it is your GPS receiver. This means that the distance could be anywhere on that circle. But this time, we have two known distances from two satellites, which two signal the precise position could be any of the 2 points where the circle intersect. Because we have a third satellite, it reveals your true location where all three cycles intersect. Using three distance, trilateration can pinpoint a precise location. Each satellite is at the center of a sphere and where they all intersect in the position of the GPS receiver. As the position of GPS receiver moves, the radius of each circle or distance will also change. But the reality is in our three-dimensional world that GPS satellite broadcasts signal as a sphere. Each satellite is at the center of sphere, where all spheres intersect determine the position of the GPS receiver. And this is the type of the signal transmitted from the satellite of electromagnetic wave. GPS signal have basically three types of signal: carrier signal, PRN code, and navigation data. As you see from the video. This is GPS code frequency, the carrier L1, the carrier L, CA code, P code, E code, and navigation message. And this is a parameter for the P code and CA code. And this the code, the modulation code with the 50 bits navigation, 50 bits per second navigation message, which composed of a set of 25 frames, where each frame include 5 subframe. And each subframe contain a clock data parameter that describe the satellite clock, and the subframe 2 and 3 include broadcast ephemeris data parameter, and subframe 4 and 5 include used to transmit different page of system data, such as the ionospheric model. And typically, GPS receiver will take the input signal at the L1 or L2 band, filter it to isolate the GPS signal from the surrounding signal, down convert the signal to intermediate frequency using a numerically controlled oscillator, and amplify the signal for digital sampling. Within an radio frequency chain, filtering and amplification are repeated as needed. GPS signals are transmitted with right circular polarization, or RCP. RCP receiving antennas are preferred so that the antenna is properly oriented to receive the signal. The common goal of any GPS antenna is to minimize or control multipath. Multipath occurs when the received signal comes from the reflection of GPS signal on the base where the antenna is mounted, or from adjacent object. This code phase technique and carrier phase method used by the GPS satellite. And GPS signal processing for the error source. Error source normally come from the control signal mistake, user mistake, receiver errors, noise and bias errors, selective availability, satellite clock error, ephemeris data, trophospheric delay, ionosphere delays, and multipath. So to reduce this error, they actually update the algorithm quite frequent. And each GPS satellite contains multiple atomic clocks that contribute very precise time data to the GPS signal. GPS receiver decode the signal, effectively synchronizing each receiver to the atomic clock. This enables users to determine the time within 100 billion of a second without the cost of owning and operating atomic clock. And GPS radio occultation, GPSRO, is a type of radio occultation that relies on radio transmission from GPS, or more generally from GNSS satellite. This is a relatively new technique, first applied in 1995 for performing atmospheric measurement. It is used as a weather forecasting tool and could also be harnessed in monitoring climate change. The technique involves a low Earth orbit satellite receiving a signal from GPS satellite. The signal has to pass through the atmosphere and get refracted along the way. The magnitude of the refraction depends on the temperature and water vapor concentration in the atmosphere. So using GNSRO globally distributed, a very precise vertical profile of atmospheric parameter as temperature, water vapor, and also electron density in ionosphere can be derived. Specific advantages of the method are all-weather, long-term stability, global availability, and high accuracy combined with high vertical resolution. So this is one example of the GPS for atmospheric measurement. The German geoscience satellite CHEM was launched on July 15, 2000 from the Russian Cosmodrome into an almost circular near polar orbit with an initial altitude of 454 km at an inclination of 87.2 degrees. The scientific project was under lead from the GFZ German. The main goals are the determination of gravity and magnetic field, and the application of the GPS radio occultation technique for precise atmospheric sounding on a global scale. The GPSRO measurement aboard CHEM were activated for the first time on February 11, 2001, and indicated already the potential of CHEM RO data to significantly improve the GPS occultation technique. And that's all. Thank you.